little bit later than our start time, typically, but nevertheless, we got a lovely cup of coffee right here. Of course, we got our curiosity, so let's get into the learning today. Go and study some more hiragana. Start out with our language practice of the day. Kiya. Okay. Obviously, it's a combination of ki and ya, as sure should be pretty obvious. Battle duo. I find it's a lot easier to do to learn the conjunctions when you already know what the individual terms mean. So it's pretty nice. Let's do some tracing real quick. And then a ya. Damn. My tracking's not on point today. But we still show up even on our worst days. It's the mindset. Kyoryu. Kyo is this. Obviously ki and then yo. Cha is TikTok emoji or TikTok whatchamacallit. TikTok logo, and ya is cha. Cho is TikTok icon, and yo.
Cho.
5 at the top hat with the seahorse. Yeah, it's a lot more confusing than, I don't know, just thinking about the signs individually. Obviously, we're going to do our tracing here. There we go. And then Nia. Obviously, this is Ni, and then Xia. Konyaku. Is that mattress? That's mattress. Nice. Nice. Perfect. Expert level tracing. Alright, this is Kyo, because ki and yo. This one is, I want to say nah. I think it is nah. No, it's ze. I recognize that this was se, but the squirt marks over there kind of made me think it was something else. You live and you learn. So is this one. G is she with the apostrophes. U is this one. Chio. Cho. Nice. T equals, so typically would be ta, so it must keep that same A sound secondary. So it's either sha or da. I'm pretty sure it's da. We've got, let's see, I know it's not chi, so it's got to be wo. Na is, I want to say this. Nice, good deal. We've got cha. Nice. I did that one without even looking at the stuff down here. This is fu, but with the squirt marks, so it's must be boo. Majin Buu. Alright, that's an A. This is ho with an apostrophe, so must be bo. De is gotta be that one. That's the one I meant to click. Oh wow. Nia is this one right here. Go is ko. So this one's typically ko, but with the apostrophes it makes it go. Nice. Show is going to be this one because of conjunction. Mu is this one right here. Be is this one. Shu. Alright, this one right here is mo because it looks like a mop. This is pa. Okay, I wasn't going to get that one, so it's a good thing we process of eliminationed it. By, B, it's got to be this one because this one is high traditionally, and then it's got those little squirt mark quotation marks right there, so it makes it by. Alright. Right here. Za, nice. We got ne. Between these two right here, I don't think it's this one. Oh, it might be. I don't know. It might actually be that 33% roll of the dice here. In that case, we'll go right here. Damn. Selling. Neko.
Neko.
Alright. This one right here. I want to say it's usually se, but it's obviously got these quotation marks, so I'll go pet. If it'll let me click. Damn. Saw in the bag. Tough. Gu. It's going to be this one right here. Su with apostrophe. That makes zoo. We got not too sure what this one is, to be honest. I know I've seen it before. It's not going to be a conjunction one because there's only one symbol. So that means we have a 50% shot between me and wa. I think it's me. It is wa. That's tough. Alright. We're getting hit with the heavy hitters today, and I'm going to need to take a sip of coffee for this one. That is Sha. Alright. This one, I. Nice. Me is me and hiragana. Pretty sure we've only learned hiragana so far, thankfully. Want to say this? No, it's not. It's this one. Alright. That is ma or ha. Sheesh, I'm not on it today. Pa. Oh, it's gotta be that one. Nice. Dope. Nice. New. Alright. Little 3-streak ski going. We got TikTok icon with the squirt marks at the top right. That's got to be G. This one is traditionally ha, but with the quotation marks comes ba, I would assume. Nice. This is re. This is kya. Let's go. Alright. 34 out of 40. Not, I mean, we obviously want to do better, but it is what it is. De. De. There. Pa. Ze. Damn. Wa. Nice. Me is this one. Zo. Okay. And then nah. Oof. Is that? Nah. Alright. Not our best run, but let's see what we get out of this pack right here. Oh shit. It's a common pull, unfortunately. Not worth a whole lot on the market, but it is what it is. Alright, I think we break off a little bit more. Yo. Because this is ni and this is yo. Let's write it. Oh yeah. Master tracer right here. And then the yo part. Boom. Easy money. Ryakugo is abbreviation.
略語
Ryakugo. Alright, let's write this. Ryoru is Ryori.
料理
Ryori is cooking. Obviously, Ri and Yo makes Rio. Not talking de Janeiro. Happy.
ハッピ
Happy. Cool little coat right there, I guess. Alright. So P is the... oh my goodness. So the degree symbol with the horseshoe is P or pi, whatever, however it's pronounced. This is poo. Kippu.
切符
Kippu. Okay, this will be a fun little tracing challenge. Skadoosh. Right there. Nice. Alright, time for the study. This is me, te, em, ma, ni, ru, ha, ho, fuck, ass. I should have got that one. Neo is this one. Oh, okay. I picked Rio. Okay, let's see what happened. Ya, no, yeah. Yo, there we go. Ga, Rio, it's this one. Fu, the apostrophe tells me that it might be O. Nice. Poo. No. This one. I usually get this one, I feel like. Given that there's no apostrophes or quotation marks, I can rule out these two, I think. Row. Nice, okay. Hi. Ne. That was a re. Okay. Ria. Ria. P. Gi. Yeah. 21 out of 24, I think it was. Not shabby, but you know, we're trying to aim for perfection here. Neo is this one. want to say ni, but I'm going to say re. Okay, nice. Ho. Ho, ho, ho. Alright. Now for the moment everyone's been waiting for. Let's rip open this pack, see what we get. Oh shit. It's actually a legendary skin. That's sick. Nice. I add that one to the collection for sure. Alright, so I guess we'll do one more focused review sort of deal. And then we can switch gears maybe into either learning some katakana or just throw a video. Do some auditory practice. It's probably gonna be a shorter stream today, but still putting the work in nonetheless. Da is that is not that nice. U with the apostrophes makes B. We got do. Do is, it's gotta be that one. Fu. Shio. Shu. Shu. Okay. Zu. Ni. This one is just destroying me now. Kind of looks like a cat too. This should be an easy one for me to get. Meh. Boo. Boo. Yo. That. This one, I think here, nice. TikTok emoji is bro. Okay. Get. Beat. It's N. Set. Mo. Hat. Key. Sue got the dump truck. G. Ria. Pu. Ka. Chi. Ta. Damn. I missed an easy one. That's on me. Fuck. Ma. Za. Sa. Gu. And Kyo. P. Pa. Z. This one. Trying to think of what this is. Low key. It's not going to be any conjunctions, I don't think. Oh, ba. Okay. Cool. Gi. Okay, nice. Missing 4, not bad, but again, we're trying to aim for better. E is, I guess this one. Okay. Ni. Ne. Da. Alright. And the pack. Oh shit. It's an elite pull right there. Let's go. Holy cow. That just changed the whole luck of today. Shit. Alright, I guess we can do a... Let's do this one. Nice sunny vibes right here.
Minasan, konnichiwa. ここは明治神宮です。お正月に神社やお寺に行くことを初詣。
Visiting shrines or temples during the New Year is called Matsu. Ooh. Matsumo. This was the I? Or no, that was either I or you.
と言います。
Let's hear what she said.
ことを初詣と言います。
Matsumore?
お寺に行くことを初詣と言います。
Matsumore?
初
I think that's what she said.
初めてという漢字で、詣の部分は神社やお寺に行くという意味です。では初めてという漢字で、詣の部分は
Oh wait, that's ha. I don't know why it took me so long to realize. So, Hatsumo something?
初は初めてという
Hatsuhachimete?
詣の部分は神社やお寺に行くという意味
Something like
で
that.
す。明治神宮はその初詣に来る人が日本で一番多い神社です。明治神宮には入り口が3つあります。私が入ってきたところは一番小
Very
さい入り
nice,
口な
clean
ので、
park.
あまり
Very
人がい
autumn
ないで
for
すね。
sure.
明治神宮はとても広いです。入り口から4分ぐらい歩いたらこの広い場所に来ました。素敵な風景ですね。その上を飛行機が飛んでいきます。
Very nice, pleasant scenery for sure.
When you write, your tone influences how readers respond. With Grammarly, just highlight your text and type how you want to.
Thanks you too for the ads. Always love that.
こっちの道は暗いので明るいところを歩きましょう。
Like the city backdrop in the right there. Very
この日は11月
what's the word I'm looking for? I guess scenic.
この日の
There's like city vibes in like a nice clean sort of way, not like some of the dirty cities we have over here.
結構暖かくて外にいるのが気持ちいい日でした。ところで皆さん、私があったかくてと言ったの。
What did she say?
ところで皆さん、私があったかくてと言ったのは聞こえましたか？あったかくてはあったかい が、もともとは
It's interesting the two right there doesn't. Oh, maybe that's one of the conjunction sort of deals
よく
we were talking about
発
the
音
other
す
day.
るのが難しいと言われる言葉です。発音するのが多分日本人にとっても難しいので、話すときはだいたいあったかいと言います。
Atakai?
また飛行機が飛んでいきます。
Must be near an airport.
どこの会社の飛行機ですかね。ちょっと見えないですね。座っている人は動画を配信しているんでしょうか。
Oh shit. Streamer in the
素
wild.
敵な背景で撮れそうですね。その手前に立ち入り禁止と書いてある場所がありました。この漢字覚えておいてください。
Entering prohibited.
立ち入り禁止です。入ってはいけませんということです。入ると危なそうですね。あそこに立っている男の人が見ているのは、もちろん飛行機です。
We're just trying to snap some angles of the planes.
同時にもう一機別の方向に飛行機が飛んでいっています。飛行機だらけです。日当たりのいいところに人が多いですね。こっちは池です。カモがいます。カモが寝ています。
It's interesting how ducks can sleep floating. They're just built different, I guess.
飛行機が飛び、芝生の上の人間たちは瞑想をしたり、何かを読んだり、寝っ転がったり、みんな好きなことをしているように見えました。
Damn, that shot with the sun is kind of crazy.
夕日が眩しいですね。夕日というのは夕方の太陽の光のことです。
It's crazy how it looks so
夕
big.
日は
That's
夏
what
は
she said, but
赤いことが多い
you
で
don't know what
す。
I'm talking about.
夕焼けとも言います。でも冬はこの日のような黄色というか黄金のような色の夕日が見られます。綺麗ですね。その上をまた飛行機が飛んでいきました。
Planes on planes. On planes.
飛行機好きな人には最高の場所だと思います。ずっと飛行機が飛んでいました。代々木方面と
Yoyogi and Harajuku.
代々木方面というのはその
Yoyogi.
方向に代々木があるということです。とりあえず代々木方面に行ってみます。
Sort of yoyogi kind of person. Makes sense.
ここの木、自然の木のように見えるかもしれませんが、人工的に植えた木だそうです。10万本の木が植えられたそうです。 その時に50年後、100年後、そして150年後にどうなっているかを考えて植えたそうです。今この森はできてから100年
Damn, ancient forest. Used to probably have battle in there at some
今
point.
は自然の森に見えますよね。計画通りなんだと思います。すごいですね。人が多くなってきました。
Damn, that spot's bumping.
観光バスも来ています。ここは代々木口という入り口です。今年の1月1日にはここから入って初詣に行きました。その時の動画はこちらです。ものすごく混んでたんですが面白かったですよ。私はさっきの広場に戻って入ってきた入り口から出ることにしました。
Damn. That made me think I had like something going on in the background. That little noise. Presumably like birds
明
or
治神
something.
宮の入り口の門がもうすぐ閉まるというアナウンスが流れていました。あそこに石があるのはわかりますか？あれは亀石と呼ばれていて、
That is. Oh,
あれは
this is called the Kaishi? Is that what that is?
のはわかりますか？あれは亀石と呼ばれていて、
Oh,
触る
Kamaichi.
と長生きできる健康な体が
Oof,
手に入る
Fortunately.
と言われているんだそうです。
See ya, buddy. Wouldn't want to be ya.
亀は長生きをする動物なので、亀の形をした石は縁起がいいんだと思います。縁起がいいというのは何か
Turtle
いい
shaped
こと
stones
が
are
起こり
considered
そう
good
と
luck.
いうような
Interesting.
意味です。
This one is the E.
飛行機が通ると
Full Sail University is where you can get hands-on experience with emerging
Oh,
technologies.
Full Sail
Whether you're
University.
飛行機が通るとどうしても上を見てしまいます。あそこにカラスがたくさんいます。
Damn, Itachi must not be far behind.
攻撃
Maybe
さ
this
れ
whole
たら
video
どう
is
しよ
just
う
one big Tsukiyomi.
ちょっとドキドキしました。でもカラスの方がどいてくれました。ちょっと悪いことをした気がしました。鳥がたくさん集まっているのを見ると、ヒッチコックの鳥という映画を思い出します。
Old
皆さん
school
見
film.
たことありますか？1963年の映画なので見たことがない人が多いと思います。 怖いですよ。鳥が理由もなく
It's interesting how scary a movie can really be, given that it came out in 1963, right?
あの映画を見た後では鳥の
Especially when compared to modern
います。
horrors that utilize our technologies and all that
出て
such.
きました。入ってきたところから出て、次は代々木公園に行きます。
Alright. Probably going to call
代々木
the
公園は地図で
auditory practice there and switch over to some Khan Academy. I know I had I made a mental note to start beginning this area on Khan Academy, since figured it'd be a good place to start.
So I have a curve here that represents
Oh,
y
this is old
is equal
OG
to
Sal.
f of x. And there's a classic problem that mathematicians have long thought about. How do we find the area under this curve, maybe under the curve and above the x-axis? And let's say between two boundaries. Let's say between x is equal to a and x is equal to b. So let me draw these boundaries right over here. That's our left boundary. This is our right boundary. And we want to think about this area right over here. Well, without calculus, you can actually get better and better approximations.
This
for it.
does sound
How would you do
familiar.
it? Well, you could divide this section into a bunch of delta x's that go from A to B. They could be equal sections or not, but let's just say for the sake of visualizations, I'm going to draw roughly equal sections here. So that's the first, that's the second, this is the third, this is the fourth, this is the fifth, and then we have the sixth right over here. And so each of these, this is delta x, let's just call that delta x1, this is delta x2, this width right over here, this is delta x3, all the way to delta xn. I'll try to be general here. And so what we could do is, let's try to sum up the area of the rectangles defined here. And we could make the height, maybe we make the height based on the value of the function at the right bound. It doesn't have to be. It could be the value of the function someplace in this delta x. But that's one solution. We're going to go into a lot more depth into it in future videos. And so we do that. And so now we have an approximation where we can say, look, the area of each of these rectangles are going to be f of x sub I, where maybe x sub I is the right boundary the way I've drawn it, times delta xi. That's each of these rectangles. And then we can sum them up. And that would give us an approximation for the area. But as long as we use a finite number, we might say, well, we can always get better by making our delta x's smaller and then by having more of these rectangles. Or get to a situation, here we're going from I is equal to 1 to I is equal to n. But what happens is delta x gets thinner and thinner and thinner, and we have an n gets larger and larger and larger. As delta x gets infinitesimally small, and then as n approaches infinity. And so you're probably sensing something. Then maybe we could think about the limit as, we could say, as n approaches infinity, or the limit as delta x becomes very, 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 very small. And this notion of getting better and better approximations as we take the limit as n approaches infinity, this is the core idea of integral calculus. And it's called integral calculus because the central operation we use, the summing up of an infinite number of infinitesimally thin things, is one way to visualize it, is the integral. That this is going to be the integral, in this case, from a to b. And we're going to learn in a lot more depth. In this case, it is a definite integral of f of x dx. But you can already see the parallels here. You can view the integral sign as like a sigma notation, as a summation sign, but instead of taking the sum of a discrete number of things, you're taking the sum of an infinite number infinitely thin things. Instead of delta x, you now have dx, infinitesimally small things. And this is the notion of an integral. So this right over here is an integral. Now, what makes it interesting to calculus, it is using this notion of a limit, but what makes it even more powerful is it's connected to the notion of a derivative, which is one of these beautiful things in mathematics. As we will see in the fundamental theorem of calculus, that integration, the notion of an integral, is tied closely to the notion of a derivative. In fact, the notion of an antiderivative. In differential calculus, we looked at the problem of, hey, if I have some function, I can take its derivative and I can get the derivative of the function. Integral calculus, we're going to be doing a lot of, well, what if we start with a derivative? Can we figure out through integration, can we figure out its antiderivative, or the function whose derivative it is? As we will see, all of these are related. The idea of the area under of curve, the idea of a limit of summing an infinite number of infinitely thin things, and the notion of an antiderivative, they all come together in our journey in integral calculus.
It's a pretty hype intro, not gonna lie. I've always been amazed at how he's able to write so steady. He must have low DPI or something.
What we're going to do in this video is introduce ourselves to the notion of a definite integral. And with indefinite integrals and derivatives, this is really one of the pillars of calculus. And as we'll see, they are all related, and we'll see that more and more in future videos, and we'll also get a better appreciation for even where the notation of a definite integral comes from. So let me draw some functions here, and we're actually going to start thinking about areas under curves. So let me draw coordinate axes here. So that's my y-axis. This is my x-axis. Actually, I'm going to do two cases. So this is my y-axis. This is my x-axis. And let's say I have some function here. So this is f of x right over there. And let's say that this is x equals a. And let me draw a line going straight up like that. And let's say that this is x equals b, just like that. And what we want to do is concern ourselves with the area under the graph of y is equal to f of x, and above the x-axis, and between these two bounds, between x equals a and x equals b. So this area right over here. And you can already get an appreciation. We're not used to finding areas where one of the boundaries, or as we'll see in the future, many of the boundaries could actually be curves. But that's one of the powers of the definite integral and one of the powers of integral calculus. And so the notation for this area right over here would be the definite integral. And so we're going to have our lower bound at x equals a, so we'll write it there. We'll have our upper bound at x equals b, right over there. We're taking the area under the curve of f of x, and then dx. Now in the future, we're going to, especially once we start looking at Riemann sums, we'll get a better understanding of where this notation comes from. This actually comes from Leibniz, one of the founders of calculus. This is known as the summa symbol. But for the sake of this video, you just need to know what this represents. This right over here, this represents the area under f of x between x equals a and x equals b. So this value and this expression should be the same.
Nice. I don't know why the video said it was 7 minutes long. Must be broken up into these little must be dispersed across this whole little lesson plan thing they got going on. Definite integral can be used to express information about accumulation and net change in applied contexts. Let's see how it's done. Thinking about accumulation in a real world context. Say a tank is being filled with water at a constant rate of 5 liters per minute for 6 minutes. We can find the volume of the water in liters by multiplying the time and the rate. Yeah, that makes sense. You get a common denominator. You multiply by minutes. Minutes cancel out, you're left with 30 liters. Yeah, that makes sense. Now consider this case graphically. The rate can be represented by the constant function R1 of t equals 5. Okay. Tank is, sorry, I'm just trying to get this visualization in my head. Say a tank is being filled with water, okay, 5 liters a minute for 6 minutes. Okay. Oh yeah, that makes sense. Alright, because it's at a constant rate. As time goes on, the rate stays the same. Yep. Each horizontal unit in this graph is measured in minutes, and each vertical unit is measured in liters. Okay. Liters per minute. The area of each square unit is measured in liters. Okay, that makes sense. I see what they're saying. So they're saying time is X, rate is Y, the point where they meet is liters. Yeah, that makes sense. Furthermore, the area of the rectangle bounded by the graph of R1 and the horizontal axis between t equals 0 and t equals 6 gives us the volume of water after 6 minutes. Yeah, that makes sense. I assume we're going to use, since this area right here is highlighted, we're going to use like an integral to find it. Maybe not, since it's a curve. Now let's say another tank is being filled, but this time the rate isn't constant. R2 of t equals 6 sine 0.3t. Okay. How can we tell the volume of water in this tank after 6 minutes? To do that, let's think about the Riemann sum approximation of the area under the curve between t equals 0 and t equals 6. For the sake of convenience, let's use an approximation where each rectangle is 1 minute wide. Okay. We saw how each rectangle represents volume in a liter. Specifically, each rectangle in this Riemann sum is an approximation of the volume of water that was added to the tank at each minute. That makes sense. When we add all the areas, i.e. when all the volumes are accumulated, we get an approximation for the total value of water after 6 minutes. Okay. As we use more rectangles with smaller widths, we will get a better approximation. If we take this to a limit of accumulating infinite rectangles, we will get the definite integral. Okay, obviously, as he said in the video, 6 is the upper limit, 0 is, I guess, the lower limit. Or, no, 0, okay. From 0 to 6 is where the area we're trying to calculate. So there's the x ranges that are our limits. And then change in t. Okay. This means that the exact volume of water after 6 minutes is equal to the area bounded by the graph of R2 and the horizontal axis between t equals 0 and t equals 6. Okay. So integral calculus allows us to find the total volume after 6 minutes. Okay. Show calculation. So when you do this, you take, oh, they just applied, they just plugged in. Where are they getting sine from? I might have to, it might be worth investigating earlier calculus just to get a refresher, not gonna lie. 6 sine of 0.3. Where are we getting 0.3 in this equation? The rate isn't constant. 6. Okay, so this is the rate. This is rate 2. Obviously, this is rate 1. 6 sine point. Okay, so that's just the rate that they gave us, I assume. So when we plug 6 sine point 3t into this, we get negative 6 over 0.3, because you took the derivative of it, I would assume. Yeah, I might have to go back to earlier calculus to get a refresher. Yeah, this might be a something we go back for. Differential calculus, derivatives basic, yeah. More. We cover integrals in this, parametric, vector values. I think we're going to actually change gears to this. Proficient, okay. Estimating limits from graphs, unbounded limits. Okay.
So we have the graph of y equals f of x right over here, and we want to figure out 3 different limits. And like always, pause this video and see if you can figure it out on your own before we do it together. All right.
A limit as x approaches negative, or approaches 6, from where? That limit could be infinite, but if we're starting it here, then the limit would only be, what, 2? As x approaches 4, could be infinite, could also be 2.
Now first let's think about what's the limit of f of x as x approaches 6. So as x, let me do this in a color you can see, as x approaches 6 from both sides, well, as we approach 6
oh, yeah,
from
there's
the
2
left-hand
limits. That's
side,
one
from
thing we need to
values
remember.
less than 6, it looks like our f of x is approaching 1. And as we approach x equals 6 from the right-hand side, it looks like our f of x is once again approaching 1. And in order for this limit to exist, we need to be approaching the same value from both the left and the right-hand side.
Okay.
And so here, at least graphically, so you never are sure with the graph, but this is a pretty good estimate, it looks like we are approaching 1 right over there. Let me do it in darker color. Now let's do this next one. The limit of f of x as x approaches 4.
What?
So as we approach section the side, 1. And as we approach x equals 6 from the right-hand side, it looks like our f of x is once again approaching 1. And in order for this limit to exist,
I'm very
we need to be
rusty in my
approaching
math
the same
skills, not
value
gonna
from
lie.
both the left and the right-hand side. And so here, at least graphically, so you never are sure with the graph, but this is a pretty good estimate, it looks like we are approaching 1 right over there. Let me do it in darker color. Now let's do this next one. The limit of f of x as x approaches 4. So
You can see
as we
there's a
approach
hole there, so
4
we'll get a case
from
of
the left-hand side, what is going on.
how this
Well, as
interaction
we approach
goes.
4 from the left-hand side, it looks like our function, the value of our function, it looks like it is approaching 3. Remember, you can have a limit exist at an x value where the function itself is not defined. The function, if you said what is f of 4, it's not defined. But it looks like when we approach it from the left, when we approach x equals 4 from the left, it looks like f is approaching 3. And when we approach 4 from the right, once again, it looks like our function is approaching 3. So here, I would say, at least from what we can tell from the graph, it looks like the limit of f of x as x approaches 4 is 3, even though the function
it's good to
itself is
know.
not defined there. Now let's think about the limit as x approaches 2.
That would be
So
2,
this is
I would
interesting. The
assume.
function is defined there. F of
But
2
there's also
is
2 values.
Let's see. When we approach from the left-hand side, it looks like our function is approaching the value of 2. But when we approach from the right-hand side, when we approach x equals 2 from the right-hand side, our function is getting closer and closer to 5. It's not quite getting to 5, but as we go from 2.1, 2.01, 2.001, it looks like our function, the value of our function, is getting closer and closer to 5. And since we are approaching two different values from the left-hand side and the right-hand side, as x approaches 2 from the left-hand side and the right-hand side, we would say that this limit does not exist. So, does not exist, which is interesting. In this first case, the function is defined at 6, and the limit is equal to the value of the function at x equals 6. Here, the function was not defined at x equals 4, but the limit does exist. Here, the function is defined at x equals 2, but the limit does not exist as we approach x equals 2. Let's do another function, just to get more cases of looking at graphical limits. So here we have the graph of y is equal to g of x. And once again, pause this video and have a go at it. See if you can figure out these limits graphically.
As x approaches 5, see it works from the right, from the left, at about, what, like a third, maybe a little bit higher. But then as we approach from the right, there's that gap there. So, no, as x approaches 7, there's that gap there.
So first we have the limit as x approaches 5 of g of x. So as we approach 5 from the left-hand side, it looks like we are approaching this value. So let me see if I can draw a straight line that takes us. So it looks like we're approaching this value. And as we approach 5 from the right-hand side, it also looks like we are approaching that same value. And so this value, just eyeballing it off of here, it looks like it's about 0.4. So I'll say this limit definitely exists. Just when we're looking at a graph, it's not that precise. So I would say it's approximately 0.4. It might be 0.41. It might be 0.41456789. We don't know exactly just looking at this graph, but it looks like a value roughly around there. Now let's think about the limit of g of x as x approaches 7. So let's do the same exercise. What happens as we approach from the left, from values less than 7, 6.9, 6.99, 6.999? Well, it looks like the value of our function is approaching 2. It doesn't matter that the actual function is defined. G of 7 is 5. But as we approach from the left, as x goes 6.9, 6.99, and so on, it looks like our value of our function is approaching 2. And as we approach x equals 7 from the right-hand side, it seems like the same thing is happening. It seems like we are approaching 2. And so I would say that this is going to be equal to 2. And so once again, the function...
In circumstances where there's a hole here and there's a solid dot up here, you take this value as the limit.
Function is defined there, and the limit exists there, but the g of 7 is different than the value of the limit of g of x as x approaches 7. Now let's do one more. What's the limit as x approaches 1? Well, we'll do the same thing. From the left-hand side, it looks like we're going unbounded. As x goes 0.9, 0.99, 0.999, 0.99999, it looks like we're just going unbounded towards infinity. And as we approach from the right-hand side, it looks like the same thing is happening. We're going unbounded to infinity. So formally, sometimes informally, people might say, oh, it's approaching infinity or something like that. But if we want to be formal about what a limit means in this context, because it is unbounded, we would say that it does not exist. Does not exist.
Okay, because so if it's unbounded like this, it doesn't exist. If there's overlap right here, like if there's overlap in dots where seemingly a hole, but then another y value, there's a solid dot, take the limit value of the hole. It's unbounded
so
limits.
Right over here, we have the graph of y
is this where we do the union
1
thing?
over x squared. And my question to you is, what is the limit of 1 over x squared as x approaches 0? Pause this video and see if you can figure that out.
Formula.
Well, when you try to figure it out, you immediately see something interesting happening at x equals 0. The closer we get to 0 from the left, you take 1 over x squared, it just gets larger and larger and larger. It doesn't approach some finite value. It's unbounded, has no bound. And the same thing is happening as we approach from the right. As we get values closer and closer to 0 from the right, we get larger and larger values for 1 over x squared without bound. So terminology that folks will sometimes use where they're both going in the same direction, but it's unbounded, is they'll say this limit is unbounded. In some context, you might hear teachers say that this limit does not exist, and it definitely does not exist if you're thinking about approaching a finite value. In future videos, we'll start to introduce ideas of infinity and notations around limits and infinity, where we can get a little bit more specific about what type of limit this is. But with that out of the way, let's look at another scenario. This right over here, you might recognize as the graph of y is equal to 1 over x.
Okay. So this is
I'm going to ask you the same
one.
question. Pause this video and think about what's the limit of 1 over x as x approaches 0. Pause this video and figure it out. All right, so here when we approach from the left, we get more and more and more negative values, while when we approach from the right, we're getting more and more positive values.
That's what it is.
So in this situation where we're not getting unbounded in the same direction, the previous example we were being unbounded in the positive direction, but here from the left we're getting unbounded in the negative direction, while from the right we're getting unbounded in the positive direction. And so when you're thinking about the limit as you approach a point, if it's not even approaching the same value or even the same direction, you would just clearly say that this limit does not exist. Does not exist. So this is a situation where you would not even say that this is an unbounded limit or that the limit is unbounded, because you're going in two different directions when you approach from the right and when you approach from the left. You would just clearly say does not exist.
Nice. Good information right there. Good knowledge. Always appreciated from Mr. Salcon. Go to the article. Okay. So important difference between the value of function is approaching what we call the limit and the value of the function itself. Graphs are a great tool for understanding this difference. Okay. Value is undefined, but the limit value is approximately 0.25. Yeah. Just remember that we're dealing with approximation, not exact value. What is a reasonable estimate for the limit of g of x as x approaches 1? As x approaches 1 from the left, it is like negative 1.25, maybe negative 1.4. We can see as you come from the right as well, that limit does exist. As x approaches 1, yeah, so it's got to be 2.4 or 1.4. Nice. Sometimes the limit value does not equal the function value. Whenever you're dealing with a piecewise function, it's impossible to get a graph like the one below. No, it's possible to get a graph like the one below. Okay, and we said in this one, the limit is defined, and it is this dot right here. So that would be roughly over 4.2, and it approaches the same place from the right as well as the left. Check that. Nice. And just because a function is undefined for some x value does not mean there's no limit to it. Holes in graphs happen with rational functions, which become undefined when their denominators are 0. So the graph of y over sine of x, notice there's a hole at x equals 0 because the function is undefined there. Okay. The limit. Okay. Yeah, that's basically just telling us stuff we already know. What is a reasonable estimate as x approaches negative 4? Negative 4. This one, the limit is going to be 3.3. Okay. Reinforcing the idea, the function value at x equals negative 4 is irrelevant to finding the limit, all that matters is figuring out what the y values are approaching as we get closer and closer to x equals -4. On the flip side, what the function is defined, when the function is defined for some x value, that doesn't mean that the limit necessarily exists. Just like an earlier example, this graph shows the sort of thing that can happen when we're working with piecewise functions. Notice how we're not approaching the same y value from both sides of x equals 3. And in this example, we would say the limit doesn't exist because they're approaching two different values, right? Irregardless of, the holes or whatever. Okay. Graphing calculators are pretty slick these days. Graphing calculators like Desmos. Okay. Can give you a feel for what's happening to the y values as you get closer and closer to a certain x value. Try using a graphing calculator to estimate these. Element of sine. I don't know how to add the suffix thing. Add slider. Expression. I don't know. This isn't like the graphing calculator I'm used to. Is it always true that limit of f of x as x approaches a will always equal f of a? No. Okay. Which statement better describes how graphs help us reason about limits? A graph can help us approximate a limit by allowing us to estimate the finite y value we're approaching as we get closer and closer. Graph is a great tool for always finding the exact value of the limit. Well, we know we can't do that, so A is a better option. Alright, good deal. Up next, exercise. Let's do this practice. Let's go. Okay. As x approaches -4, the limit does exist. -5.2. Okay. Alright, good deal. As x approaches 4, f of x, we would still say is this hole right here, which is a little under 7, 6.7. Okay. That was a reasonable estimate for limit of f of x as x approaches 1. As x approaches 1, this is the same value as well, so roughly -4.5. Okay. Limit of g of x as x approaches 5. When they go in two different directions, the limit doesn't exist. Okay, nice. Hey, cool little jingle. Go fill up on some coffee real quick. I will be right back. back. We're gonna just probably go till this one-sided limits from graphs. Complete that, and then I think we'll be on our
So if we
on
were
our
to
way
ask
with our day.
ourselves, what is the value of our function approaching as we approach x equals 2 from values less than x equals 2? So as you imagine, as we approach x equals 2, so x equals 1, x equals 1.5, x equals 1.9, x equals 1.999, x equals 1.9999999, what is f of x approaching? And we see that f of x seems to be approaching this value, right over here. It seems to be approaching 5. And so the way we would denote that is the limit of f of x as x approaches 2, and we're going to specify the direction. As x approaches 2 from the negative direction, we put the negative as a superscript after the 2 to denote the direction that we're approaching. This is not a negative 2. We're approaching 2 from the negative direction. We're approaching 2 from values less than 2. We're getting closer and closer to 2, but from below, 1.9, 1.99, 1.99999. As x gets closer and closer to from those values, what is f of x approaching? And we see here that it is approaching 5. It is approaching 5. But what if we were asked a different question, or I guess the natural other question? What is the limit of f of x as x approaches 2 from values greater than 2? So this is a little superscript positive right over here. So now we're going to approach x equals 2, but we're going to approach it from this direction. X equals 3, x equals 2.5, x equals 2.1, x equals 2.01, x equals 2.0001. We're going to get closer and closer to 2, but we're coming from values that are larger than 2. So here, when x equals 3, f of x is here. When x equals 2.5, f of x is here. When x equals 2.01, f of x looks like it's right over here. So in this situation, we're getting closer and closer. We're getting closer and closer to f of x equaling 1. It never does quite equal that. It actually then just has a jump discontinuity. But it seems to be approaching, this seems to be the limiting value when we approach x from values greater than, or when we approach 2 from values greater than 2. So this right over here is equal to 1. And so this is, and so when we think about limits in general, the only way that a limit at 2 will actually exist is if both of these limits, both of these one-sided limits are actually the same thing. In this situation, they aren't. As we approach 2 from values below 2, the function seems to be approaching 5. And as we approach 2 from values above 2, the function seems to be approaching 1. So in this case, the limit, let me write this down, the limit of f of x as x approaches 2 from the negative direction does not equal the limit of f of x as x approaches 2 from the positive direction. And since this is the case that they're not equal, the limit does not exist. The
Makes
limit
sense.
as x approaches 2 in general of f of x, so the limit of f of x is the limit of f of x as x approaches 2 does not exist. Does not exist. In order for it to have existed, these two things would have had to been equal to each other. For example, if someone were to say, what is the limit of f of x as x approaches 4, well, then we can think about the two one-sided limits, the one-sided limit from below and the one-sided limit from above. So we could say, well, let's see, the limit
As
of f
above,
of
so
x
below.
as x approaches 4 from below. So let me draw that. So we care about x equals 4. As x equals 4 from below, so when x equals 3, we're here, where f of 3 is negative 2. F of 3.5 seems to be right over here. F of 3.9 seems to be right over here. F of 3.999. We're getting closer and closer to our function equaling negative 5. So this, the limit as we approach 4 from below, this one-sided limit from the left, we could say, this is going to be equal to negative 5. And if we were to ask ourselves the limit of f of x as x approaches
Would that not also
4
be negative
from
5?
the right, from values larger than 4, x approaches 4 from the right, well, same exercise. f of 5 gets us here. F of 5 or f of 4.5 seems right around here. F of 4.1 seems right about here. F of 4.01 seems right around here. And even f of 4 is actually defined, but we're getting closer and closer to it. And we see once again we are approaching 5. We are approaching 5. Even if f of 4 was not defined, on either side we would be approaching 5. Or sorry, we'd be approaching negative 5. So this is also approaching negative 5. And since the limit from the left-hand side is equal to the limit from the right-hand side, we can say, so these two things are equal, and because these two things are equal, we know that the limit of f of x as x approaches 4 is equal to 5. Let's look at a few more examples. So let's ask ourselves, the limit of f of x, now this is our new f of x depicted here, as x approaches 8, and let's approach 8 from the left, as x approaches 8 from values less than 8. So what's this going to be equal to? And I encourage you to pause the video to try to figure it out yourself. So x is getting closer and closer to 8. So if x is 7, f of 7 is here. If x is 7.5, f of 7.5 is here. So it looks like our value of f of x is getting closer and closer and closer to 3. So it looks like the limit of f of x as x approaches 8 from the negative side is equal to 3. What about from the positive side? What about the limit?
So we see that there is a disparity in the limit
x
too.
Approaches 8 from the positive direction or from the right side. Well, here we see as x is 9, this is our f of x. As x is 8.5, this is our f of 8.5. It seems like we're approaching f of x equaling 1. So notice these two limits are different. So the limit actually does the non-one-sided limit or the two-sided limit does not exist at f of x or as we approach 8. So let me write that down. The limit of f of x as x approaches 8, because these two things are not the same value, this does not exist. Does not exist. Let's do one more example. And here they're actually asking us a question. The function f is graphed below. What appears to be the value of the one-sided limit? The limit.
All right, so we're going to do this before he does, try and get some practice, work through our thought processes. So what appears to be the value of the one-sided limit, f of, as x approaches negative 2 from the left. So as x approaches negative 2 from the left, we can see that that limit is going to be 4. And it doesn't matter that it's not filled in because that's a limit. It's not a real value. And yeah.
Limit of f of x, this is f of x, as x approaches 2 from the negative direction, or sorry, as x approaches negative 2 from the negative direction. So this is the negative 2 from the negative direction. So we care what happens as x approaches negative 2. We see f of x is actually undefined right over there. But let's see what happens as we approach from the negative direction, or as we approach from values less than negative 2, or as we approach from the left. As we approach from the left, f of negative 4 is right over here. So this is f of negative 4. F of negative 3 is right over here. F of negative 3 is right over there. F of negative 2.5 seems to be right over here. We seem to be getting closer and closer to f of x being equal to 4, at least visually. So I would say that it looks, at least graphically, the limit of f of x as x approaches 2 from the negative direction is equal to 4. Now, if we also ask ourselves the limit of f of x as x approaches negative 2 from the positive direction, we would get a similar result. We're going to approach from when x is 0, f of x seems to be right over here. When x is 1, f of x is right over here. When x is negative 1.99, this was when x is negative 1, f of x is there. When x is negative 1.9, f of x seems to be right over here. So once again, we seem to be getting closer and closer to 4. Because the left-handed limit and the right-handed limit are the same value, because both one-sided limits are approaching the same thing, we can say that the limit of f of x as x approaches as x approaches negative 2, and this is from both directions, since from both directions we get the same limiting value, we can say that the limit exists there and it is equal to 4.
Nice. All right. Pretty straightforward. One-side limits from
Over
graphs
here we have the graph
asymptotes.
of
Alright.
y is equal to g of x. And what I want to do is I want to figure out the limit of g of x as x approaches positive 6 from values that are less than positive 6, or you could say from the left, from the, you say, the negative direction. So what is this going to be equal to? And if you have a sense of it, pause the video and give a go at it.
As x approaches 6 from the negative direction. We could say 6. But at the same time, there's 2, so I don't know.
Well,
I guess it would be
to think about this,
6.
let's just take different x values that approach 6 from the left and look at what the values of the function are. So g of 2 looks like
it's either infinity. As x approaches 6 from the negative direction, it's infinity. And as it approaches from the left, or from the right, from the positive direction, it's 3. So that tells me the limit doesn't exist, but if we're just taking the one side, then it...
a little bit more than 1. G of 3, it's a little bit more than that. G of 4, looks like it's a little under 2. G of 5, it looks like it's around 3. G of 5.5 looks like it's around 5. G of, let's say, 5.75 looks like it's like 9. And so as x gets closer and closer to 6 from the left, it looks like the value of our function just becomes unbounded. It's just getting infinitely large. And so in some contexts, you might see someone write that. Maybe this is equal to infinity. But infinity isn't an... We're not talking about a specific number. And if we're talking technically about limits, the way that we've looked at it, you'll sometimes see this in some classes. But in this context, especially on the exercises on Khan Academy, we'll say that this does not exist. Not exist. This thing right over here is
noted.
bounded. And this is interesting because the left-handed limit here doesn't exist, but the right-handed limit does. If I were to say the limit of g of x as x approaches 6 from the right-hand side, well, let's see. We have g of 8 is there, g of 7 is there, g of 6.5 looks like it's a little less than negative 3. G of 6.01, little even closer to negative 3. G of 6.000001 is very close to negative 3. So it looks like this limit right over here, at least looking at it graphically, it looks like when we approach 6 from the right, looks like the function is approaching negative 3, but from the left, it's just unbounded, so we'll say it doesn't exist.
All right. Nice. Good little informative video. Let's go to the exercise and see if we can improve upon our last attempts. As x approaches negative 2 from the negative direction, that limit will be 6, negative 6. Okay, nice. As x approaches 6 from the positive direction, that would be negative 5. Okay. As x approaches 3 from the positive direction, unbounded. As x approaches 4 from the positive direction, we get 5. The limit would still be 5. Nice. Cool. Oh yeah. Easy money. Alright, yeah, I think that's what we're gonna call it for today. Nice little knowledge sesh. But yeah, hope everyone has a great day. See ya.